Verilog code based on parallel input, parallel output shift register. Before going into the Verilog code, let us discuss about what is parallel input, parallel output shift register. We may know that the shift registers are mainly of four types, that is serial input, serial output, serial input, parallel output, parallel input, parallel output, parallel input, and serial output. Today we will discuss about parallel input, parallel output shift register. Basically, the shift register means the register which shifts the data between it. Here we can see that the shift register consists of 4D flip-flops which uses for shifting of data. Here we have a clock signal which is provided to all the flip-flops at a time, and as we said here, parallel input, parallel output, the flip-flops are synchronous to each other. That means the flip-flops does not have connection in between them. That is, each flip-flop is individually connected to input and output is taken individually. See here, for 4 flip-flop we have 4 inputs and we got the outputs as 4 outputs. This means that we have given the inputs parallelly and taken the outputs as parallelly. So that's why this is called as parallel input, parallel output shift register. So here we can see that the parallel input parallel output shift register can also be used as a temporary storage devices, and in serial input serial output shift register it acts as a delay element, whereas in parallel input parallel output shift register it is used as a temporary device storage, and it can also act as a delay element. Now let us go into the Verilog code of this parallel input and parallel output shift register. Here in this we can see that this is the RTL coding and this is the test bench coding. Coming to the RTL coding, first we will define the time scale for the code, that is 1 nanosecond for 1 picosecond time precision. Here we have taken the module as PIPO underscore register, which is given as module name, and here we define the inputs and outputs, that is clock signal, clear signal, and D and Q variable. Here the clock and clear are given as the input variables, and this Q is given as the output register array format. That is, we have four Qs in the for the each flip flop. That's why we have taken it as the array format, and we have four inputs and which we have taken in the array format. And by using the always at the rate passage of clock, we have written the code. That is, when the passage of clock occurs, then our code starts. In the begin end block we will give a condition that if clear occurs, then we will find that the output is equals to the four zeros. Otherwise the q is assigned with the d input, and we will end the begin block and we will end the module. This is the RTL. And coming to the test bench, this is the test bench of the parallel input, parallel output. Here we know that in RTL the inputs and outputs which are defined, coming to the test bench they are given as outputs. If for example, if we given clock and clear as input here, coming to here we can observe that, I mean, if clock and clear are given as white type, then coming to test bench, we will get that clock and clear as registered type. We know the default function is a wire type, so we didn't mention here wire. Whereas coming here, these are defined as the reg type because default is changed. Here we can see that Q is given as wire type, whereas in RTL we have given it as the reg type. The same for D. So first we have to instantiate the RTL in the test bench. So we have used the instantiation like this by using a DUT. The clock is instantiated. The variables which are inside the braces defines the test bench components, and which are outside the braces defines the RTL components. So next we should write an initial and begin end code, in which first we have given the clock as 0 and clear input as 1. After 5 seconds, the clear is after 5 seconds of delay, the clear is converted to 0. That means the operation starts. And for each every 5 seconds of delay, we will find this operation happens. First delay is given as 0011, and next 0111, and next 1011, and next 1001, and next 4 ones, and next 0001. And for every 1 second, That is for every one after clock is negotiated. For every one clock cycle, clock is negotiated. And we will give the dollar monitor. This dollar monitor displays as the every change which happens in the code. After 150 clock cycles, we have the dollar stop and our module is ended. If you observe the waveforms here for our code, we will observe the waveforms like this. This is the clock given if clock is 1 and clear is 0. And what's the Q output is given, we get the same D output. That means parallel input, parallel output. We have given input parallelly and we have got the output parallelly. That is the meaning of this. Here, if you observe this, the clock is 0 and clear is 0. So there is no values for Q and there is no values for D also. Here, if you observe, we have the clock as 0, but we have clear as 1. So we will get the output Q as all zeros, even if we didn't give the output D. So the same can be observed in this table. Here, if you observe, we have given the data input as undefined. We get the output as undefined. Here, undefined. Here, we get the all zeros. This is because we have given the clear as 1 at this time. If you observe this, if we have given as the data input, and the same we observe, obtain the data output. This is the transcript of this window. While coming to the synthesis report, here we can observe that this is the synthesis report of the parallel input, parallel output shift register. We have taken emacs and it is given as a clear input and data input and one input, and these are given to the D flip flop, the clock and D output, and here we get the Q output. This is the simulation and synthesis and the Verilog coding of the parallel input, parallel output shift register. Thank you.